sharing the screen, and so on. All right. So magnetism, I think you'll find this a bit of a step back. What grade were you in when you heard about magnetism first and you talked about domain theory and stuff like that? Has that been done in elementary school? Anybody?
I don't remember it.
No,
So,
like even just as basic as like that likes repel each other, two norths repel each other, north and a south attract each other, that kind of stuff. Anything like that at all ever?
well, not the north and south.
Okay. I kind of feel like it's been talked about. Maybe not though. I should have asked that.
In grade 9, we talked about like attraction of particles and stuff.
So that would just be electric though, like static.
Yeah.
Like, yeah.
But nothing magnetic. I don't remember.
No. Okay. Well, fair enough. It doesn't really matter. You're going to see it here, and I just feel like it's. I don't know. For some reason, I feel like it's been done, but maybe not. Correct me if I'm wrong in the end when you see it. So here we go though. Magnetic fields, and then we're going to talk about electromagnetism as well. Anyway, starting out with magnetic fields though. I don't know if the electromagnetism in this one at all. So the first law of magnetic poles, of course, is that opposites attract and likes repel. So I don't feel like that's new info for everybody here, but I could be wrong. You just kind of automatically know because you played with magnets maybe or whatever, right? But so the push and pull with magnets, is related to what we've talked about, right? This is how we kind of naturally go to this next thing, right? Because we're talking about that push and pull can happen at a distance. We're talking about because it has fields and so on, and saying it has a field isn't really explaining anything, but the math that goes along with what you're going to see later on, you're not going to be required to do all the math, but basically you're going to get introduced to the idea of the math of field theory and exchange particles. So you've seen it a little bit already, but you'll just see it again and kind of mentally prepare yourself for when you actually try and take it on, right? Later physics class. So magnetic fields, these are action at a distance, right? As well, action at a distance, which just means, of course, there's a force without contact, right? So I'm going to say like non-contact force. So we've been talking about the electric fields and electric forces, and so it's not a big surprise that forces can happen at a distance and without contact. So just as with gravitational, electric, magnetic fields and so on, we can visualize field lines, the direction of the magnetic field, force field, and the field lines and so on can be indicated by a test compass, which is kind of like that positive test charge, right? So basically put a little compass in place and see which way north points. Okay, so that's what this next one's going to be. Is the direction of a magnetic field line by convention is the direction that a north pole of a compass would point. So north pole of a compass points. So I'm going to bold that part there. Mess up my paragraph structure here. It's dangerous. There we go. It's survivable. All right, so the direction a north would point if it was put into that field. Okay, so you've played with compasses, they point, like the red end of the compass, the north end repels away from a north end of a magnet, things like that. Hopefully it's something you've had a chance to sort of play with a little bit, but I'll be describing all of this. So you picture a bar magnet where it has like a north on one end and a south on the other. If you put a compass here, then the north end would repel away from the north end of the magnet because likes repel. So you'd have a north that would be pointing like that. So, picture a compass. If you put it here, try and draw a compass. It's not letting me draw. Why not? Is my battery dead? Huh. Man, these batteries die fast. I have spare batteries. Shouldn't need it already, but let's see. Still not working. Nope. Bear with me for a sec here. I'm just gonna grab a new battery. these pens for these laptops take quadruple A batteries, 4A. They're like even skinnier than triple A's. So I had to get the school to order some from Amazon, and I'm glad they're in already because that one seems to have died. Yeah, there we go. We're working. All right, new battery. So the north end, picture like how a north would repel away from the north end of the magnet. So you put a little compass there and it would point to that direction of the field. If you go on the other side here, it would point the same way as well. So you get magnetic field lines around magnets. And you can visualize field lines in different ways. I didn't actually ever mention that you can visualize electric fields as well. It's kind of gross, but they actually sell basically like the shaving dust from when someone shaves, all little pieces of whiskers, and you can put it in oil, and you can put an electric field, and the little whiskers will line up along the electric fields lines. And so this actually is similar to that, except it's actually not as gross because it's just little pieces of iron filings. So if you take a iron nail and rub it against a file and get a whole little bunch of little chunks of iron, those little chunks of iron will become magnetic when they're in a magnetic field, which we'll talk about shortly. And then they will basically go end to end in this. So picture a little piece of iron and how it becomes magnetic itself. So it has its own little north and south. And then if you had a whole bunch of those, like we have when we have a bunch of iron filings, so I'm just going to make a few of those, how they would all attract to each other. Right? So north to south, and so on, they would attract. And so they end up forming kind of like this, right? So if I shrink this down enough, I can kind of show the idea of why those lines are appearing in the iron filings. So like that. That's why that happens, okay? Now we have to talk a little bit about how the iron becomes magnetic as well, which is magnetic induction and so on. And we'll talk about that as well shortly. So what I had keep in mind, oh yeah, it looks very two-dimensional, but they're actually kind of very three-dimensional things. I believe these are YouTube links that hopefully just work quick because I don't necessarily want to find the video on my USB disk. Yeah, so this is a more three-dimensional demonstration of it, where you've got this like cube or rectangular box with oil and iron filings and a little channel that you can stick a magnet into. And so you can see, you stick the magnet into it, they form into field lines because those little pieces of iron are getting magnetized, and then they start to line up north to south, and you see these lines that are going. It sped it up a little bit for us there, but all these lines, pretty cool, right? I don't have one of these. I'm surprised I haven't thought of getting the school to buy me one of those because it's pretty cool. It's kind of neat to see. I will order that next order. Try to anyway, see if they'll let me buy it. And what's this one? What's this one? Question for you. Can you hear the weird music?
I can hear it a bit, yeah.
You guys hear? You can hear it? Okay, we don't need the microphone plugged in. Perfect. So this is just a this is actually a neat little apparatus too. It's got a whole bunch of little magnets, I guess, right? I don't know if it's real or not. If it's animated. It's hmm.
Mr. Horn, I'm not sure if it's just me, but I can't hear anything. It might just be my internet, but
No, I can't hear anything either.
Oh, I thought you said you could.
I could at first, but now I cannot. I thought it was just my internet, but
Yep.
it's not
Okay.
based.
I will plug in the fancy microphone and see if that fixes the problem here. Fancy mic is online, I believe. You can hear me at least.
Yeah.
And you can hear the video now.
So we have around 200
Yeah, I can hear it now.
Okay,
of the
perfect.
field demonstrator. Don't see the magnetic field at all. But if you bring it up near
So he said
the
there's
magnetic
we have a magnet and it's listed as having a north and a south pole.
field demonstrator, you'll see that the little compass needles
So when you,
align themselves.
if I were to pause it at some point and you had the north here and then it aligns a certain way, you can picture this one like the north is this end of it and the south is that end of it. The south is attracting to the north is repelling from the north, you know? That's what's going on there. I'm just going to jump ahead a little bit for when he actually puts it in there. And they really form into field lines there.
There we have it. Magnets come out of a north pole and loop around into a south pole.
Okay, so we can really
magnet shape.
See the field lines really easy with things like this. So he's going to look
The
at a
big
horseshoe
question
now.
is, what will the magnetic field lines look like?
So see how it's a north on one end of the horseshoe, and so it's basically like a bar magnet. It's north on one end, south on another, but it's like bent into a horseshoe shape. So if you picture what's going to happen here, if this is a strong north and that's a strong south, if there's a compass in here, of course the north end of the compass would repel away, and so there's going to be a lot of lines like right from one to the other, right? And then a compass here might repel from here, but eventually if you get close to here, it's going to attract to there. So you're going to actually get these curves. You can picture why you'd get these curves. So the field lines for this are going to look a heck of a lot like the field lines for two opposite charges. Got two opposite magnetic poles, two opposite charges. There's a heck of a lot of similarities here. So let me jump ahead to when he gets to that.
To the side and slide.
So you want to picture the
give it a little tap.
The fields lines going straight from one to the other, right? From the north to the south.
There we have it.
So
area is a little weak.
That is kind of neat. All right. I don't think I'll order that one though. It looks a little finicky when he's tapping the glass and stuff. So just to look at the history of magnetism just a little bit, just for fun, you know, like ancient Greeks, you know, played around with, they found some magnetic things, and as early as apparently before that, Chinese knew about strange rare stones that it says here possibly chunks of iron that had been struck by lightning. I don't know about that, but they had the power to attract iron, so they knew there was attractions. So the steel needle rubbed with a lodestone or whatever, they called these things lodestones, became magnetic as well. They kind of figured out that you could take a piece of steel and you could like just rub a magnet against it and it would become magnetic as well. And then they even discovered that if you let a magnetized piece of metal be free to rotate, it'll actually point towards the north end of the earth. So they discovered compasses. Whenever date this was, doesn't say, but it was, you know, a long time ago, right? So basically the compass obviously was a really, really valuable tool, and it kind of, you know, the technology spread pretty quickly where it's like, hey, check this thing out. This will help you figure out where you need to go. So the compass was huge in helping navigation be more reliable. And then what does it say? 1600. They basically realized that the Earth is magnetic as well, and that's why the compass points a certain direction. Still not super well understood how that magnetism even exists. It's like you have this molten core, and we've got, you know, moving charges inside apparently, and that's going to link to things we're going to learn in this course soon. But the actual organization, the mechanics of like the magnetism of it is kind of weird to do with Earth itself. It actually moves around a little bit, you know, like it's not truly at the North Pole of rotation at all. It's actually a little off from it. And then lots of things to learn about magnetism, but we're not going to do every little detail. Just introducing the ideas of it. So with modern magnetism, we're not digging up lodestones by chance and finding things that are magnetic. Instead, we've gotten pretty good at controlling it and knowing how to use it and make it and so on, right? So they're made of alloys of iron and cobalt and nickel, and you'll hear neodymium magnets. You'll hear like different names of types of materials. Yeah, so obviously we know the magnetic field is strongest to the poles, and we've got the field lines showing again there. So the kind of materials that are magnetic are like kind of a small group there in the transition metals. So the iron, cobalt, and nickel, just to relate to chemistry information that you've talked about before. So those, I want you to make a note of, the idea that we call those ferromagnetic in red there. So ferromagnetic are materials that are attracted to magnets, because not all things are, okay? Very few things are actually, really, if you think about it. It's just that we have a lot of things in life that are made of steel and it has iron in it. So we think, man, a lot of things are magnetic, right? But it's just we use steel a lot. So ferromagnetic, out of 118 elements, we've got like 3. And then other types, so we've got, that's just ferromagnetic again, right? So the iron and cobalt and nickel are magnetic. So we refer to them as having high magnetic permeability, which means to permeate means to like spread through, right? So when you say magnetic permeability, we're talking about like the magnetic field lines go through it. So I want you to picture a north and a south, and you've got these magnetic field lines that would go around and so on, right? And what happens is if you bring a piece of iron in, so let's say this is a big chunk of Fe, right? If you bring it close by, what happens is the magnetic field lines like to go through the iron even more. Like they find it easier to go through the iron than they do to go through the air. And so these field lines wouldn't necessarily be shaped exactly like that anymore. They're going to be like, oh, this is great. We can go through here like crazy because it's permeable. The magnetic field can go through the iron easier. So goes through easier, and that's why there's an interaction, right, between magnetic field of the magnet and iron when you're bringing close, and same for cobalt and nickel, of course. So we'll see magnetic permeability numbers soon as well, so think of it as like to do with how easy it goes through. So paramagnetic are things that only help magnetism a tiny little bit. So oxygen actually becomes magnetized a little bit. Oxygen itself, weird, right? But that's actually a little bit affected by magnetism. Aluminum is very, very, very slightly, like it basically behaves as if it's not magnetic. So it's only very, very slightly greater than 1. The numbers to the permeability we'll talk about in more detail in a second. Okay. This one, these numbers of permeability can be very big, and that's actually like a multiplier basically of what the magnetic field strength is. So these are only increasing the strength a tiny little bit. So we got ferromagnetic or ferromagnetism, we've got paramagnetic or paramagnetism, and then we have diamagnetic. So things like copper and silver and things like that, they actually cause a slight decrease in the magnetic field. And these are, it's hard to sequence this stuff because there's so many things. Like I kind of have to talk about the magnetic field of a coil, but we can just think of it as the magnetic field of anything, really. Like if you have a copper and silver near a magnet, it's actually going to kind of reduce the magnetism in that area. Okay, so this mystery of magnetic field of a coil, what are we talking about? We'll see that soon. So I'm combining stuff from the 3U class into here, and in the 3U class, I guess we probably would have talked about coils already, but I don't know, it seems odd because I usually would cover magnetism first rather than jumping right to electromagnetic induction, which is when magnetism is created by electrons flowing. So that's what we're going to end up covering. So anyways, diamagnetic stuff of copper and silver, just very, very slight. Notice this is slightly, right? It'll decrease the magnetic field slightly, not really blocking the magnetic field much at all. There's a little video I have that related to that. So this is the K value, like I said. So it's actually a multiplier. It's the magnetic field with that material present versus if there isn't, right? So if you have a magnetic field and you don't have iron, then you just have the regular magnetic field in a vacuum. And again, they're still talking about of coils of wire, but we'll put it all together soon. But it's a multiplier. And so if Nina said there, we'll look at solenoids soon. I just wanted to talk about permeability as a concept. But it makes the magnetic field stronger or not as strong. So if we have a permeability here of greater than 1, then of course it's making it stronger. So let's say, yeah, magnetic force becomes greater, right? If it's greater than 1, so a number like 10, for example, it's going to make the field 10 times as strong. So if the field is normally 1 and this is 10, you can see it's going to make it 10 times stronger. We talk about slightly less than 1, and so it can also make it weaker. So if it's less than 1, we really only see like 0.9 kind of 0.99 kind of numbers, right? So it's a slight reduction. And we have numbers on the next page that I might have to come back and correct this, but they're not very small. So these are permeability numbers. So a vacuum is by definition 1. It's just the standard magnetic field strength or ease that magnetic fields can go through, I should say. So you can see water and copper, and the other one on here should have been listed as well, silver. I don't have the silver listed on here, but water and silver would probably be similar. Okay, they're going to reduce slightly. So reduce magnetic fields slightly. Now that isn't too, you're not really going to see much, right? With that one, because it's reducing it by only a tiny little bit. Same with aluminum. You're going to see any magnetic effects with aluminum? No, it's like increasing magnetic fields like to go through aluminum the slightest little bit more than they like to go through air. And so aluminum doesn't really react to magnetism. Whereas if you look at iron, man, magnetic fields like to go through iron 7,000 times as much as they like to go through air, right, or a vacuum. So there's a huge effect there. So if you think about these weird substances, perm alloy and nanoperm and whatever the heck this stuff is, these you could think of as like maybe materials that maybe like NASA might employ to make magnetic effects strong enough to do some of the crazy things they try and do with their missions through that they have. Right, so I'm gonna just leave that as like a question mark there. But you picture like if you need a really strong magnet, get some of this nanoperm, and like all of a sudden now you've got a magnet that's gonna be 80,000 times as strong as it would have been if you didn't have it as part of the structure. So kind of neat. So domain theory, which I thought for sure you would have heard of, but it's not really that complicated of a thing. But basically, I'm going to tell you something about ferromagnets, and it's actually related to the idea that up here where I had said that you could rub a magnet against a piece of metal and it becomes magnetic. And up here I talked about how, wherever it was here, that a piece of iron becomes magnetic. It's because the theory, they call it domain theory, they describe it as if iron has little groups of where the magnetic field in the material, okay, spoiler alert, the magnetic field's coming from the atoms. And so if the atoms are all aligned in the same direction here, so they're all to the right here, the dots actually mean out of the page. We'll be using that soon. So this is out of page towards you, like the tip of an arrow, we think of that as like the point of an arrow coming towards you. And then this in here is little X's, and those are actually like the tail feathers of an arrow. So picture like, whatever. And so this would look like a point if it's coming towards you, and this would look like an X if it was coming towards you. Okay, so if the arrow is coming towards you, it's a dot. If the arrow is going away from you, it's an X. And so this one is into the page. So they're doing this in a very three-dimensional notation. My drawings in the homework sets, I don't bother. I just do left, right, up, down on angles, whatever. But they're being more honest here about having a bunch of different directions. So picture a block of iron, and on its own, the magnetic fields that are actually coming from the atoms. These are magnetic fields from, yeah, atoms. So atoms, magnetic fields, interact with their neighbors and align in little domains, little groups. Okay. Ferromagnetic materials do this, and also these groups can easily be convinced to all line up in the same direction. So that's the next slide here, is that a ferromagnetic material, you know, you can easily convince a ferromagnetic material to have all of those domains all line up in the same direction. And what you've got is a bunch of norths and souths all lined up, right? So you can see here that this substance here, this chunk of iron that has the fields all lined up, right? It's going to have a whole bunch of norths and souths that are all going to combine, and you're going to have an overall, very convincing overall north and south, because they're all adding up, right? So they can easily align themselves. These dipoles, or these dipoles as a south-north pair, right? They can easily align themselves if their ferromagnetic materials can do this. So you take a piece of iron that's like this, just put a strong magnetic field near it, rub it against it, whatever. These all start to flip to the right and end up all aligned. And so the iron itself becomes super magnetic. Okay. That's kind of explains the mystery of how you can make just an iron steel or iron nail into a magnet, and then pick up other things with it just by touching it with a magnet. Yeah. So this is review. This is just the magnetic law of magnetic poles, where we have repulsion from likes and attractions to whatever. So I'm skipping over that one. Magnetic. Some of this is redundant here. So magnetic fields. We've already talked about this. We didn't mention though the more field lines, the stronger the field. But I think you're thinking, yeah, I already know that, right? Because that's the same as with electric fields. So for a lot of what we're looking at here, you're just going to be like, well, that's the same as electric fields. And so this isn't really that crazy of a lesson for us, because it's just applying the idea. It's just magnetism now instead of magnetic fields instead of electric fields. The direction of the line represents the direction the north would go. We've already said that. Magnetic field lines don't begin or end. They always close as a loop. That's a little bit different. Okay, because you know, with electric fields, remember, let's say recall here, you can have a positive charge, and then the electric field lines just went out, right? And so that's you know, this statement here, number 3, isn't true for electric fields, but you can't have a south without a north. And so you always have, and I'll show you why, but you can't have a south without a north. And so the magnetic field lines always kind of go from a south to a north locally. Okay. Magnetic field lines never cross one another. Do you know why that is? It's something we've talked about recently. Do you remember why that is?
Is it like because that's like the net magnetic force and you can't have 2 of those?
Absolutely, 100%. Ding ding, good job. Winner, winner, chicken dinner, as they say, right? So yeah, absolutely. They represent the net force, and so you can't have more than one net force. So it wouldn't make sense for these lines to cross each other, because then you'd be saying, if this line went through here like this, then this line saying the net force is this way, and this line saying the net force is this way. You'd be like, you can't have 2 answers to net force. Net force is when you just add up all the forces. You can't have two different answers for the addition of all the forces at a given spot. Perfect. Good job, Sarah. All right. So that questions so far? Like, am I right that this is kind of? Do you already know this, or is this really, really new?
No, it's really, really new, unless like I have amnesia from a certain grade or something like that.
Fair enough.
I feel like the overall topic is like kind of like we've heard of it before, but like the details are new, I guess. Does that make sense? I don't know.
Yeah, I think I know what you mean. You're familiar with magnetism, but now you're like learning how it kind of works. Does that make sense? Yeah.
Yeah.
Okay, so, but I think we could agree that it's not like mind blowing, right? It's like, oh, okay, I get it. That kind of explains how magnetism works, and so I'm hoping this is a bit of a step back in stress level for us. Where we're just like, oh, okay, I get it. We're applying our ideas of magnetism or of fields to this new thing. So like when we look at the attraction field and the repulsion field, this is the same diagrams as we saw with charges. So it's not new. It's nice that we just apply the idea, right? We know that it would make sense. So parallel, what is a parallel magnetic lines of force? Oh, yeah, parallel magnetic lines of force in the same direction repel one another. That's really not, I don't really like the wording of that, but anyways, it looks like that, right? And then they attract each other. Parallel lines of force in opposite directions tend to unite. Yeah, so you'd have a parallel, you'd have a line here. What they mean there is that your north would be going this way, and this north would be going this way, right? And so they kind of, these two lines kind of connect, because on its own, we would have had a south that would have been like this, right? But when we brought the north in here, right, we have a north line going up like this. So then this one's like, oh, you know what? I'm okay with joining forces with that sucker, and like that's kind of how that's happening. So how do they word that? Parallel lines, forces in opposite directions. Yeah, they say opposite directions. Single electron. Does that not seem kind of odd that it's saying opposite directions? I think that should say same direction, shouldn't it? What do they mean by that? Because I'm thinking like these were both the same direction, and so they're uniting. But I know what they're saying here, that they have like these are going the same direction here. But you know what? I think this should have been, they should have reversed those from how I'm interpreting this, the way they're wording it, because here we had these are opposite directions, and so they repel. So let's change that based on this interpretation, right? These are opposite directions, tend to repel one another. That's the blue stuff there. And then I'm going to color code things here, make this be like green or something. Come on, green. Why are you doing that to me? Maybe it's my pen thing again. Yep. Greeny green. Here we go. So the opposite. Oh, darn it. We kind of little subtle differences trying to work with a touch screen instead of a smart board. Lock in place. All right. So opposite stuff, and we'll just make these be. That's going to say same instead. Right, because down here we had the same direction stuff going on. I maybe should use a mouse that doesn't have Bluetooth and see if that changes my conflicting Bluetooth fields. But they're same direction and they're joining forces. There's opposite direction. They're repelling. Magnetic lines of force always enter or leave at right angles to a surface. Whatever, who cares? But they're not really showing that, are they, though? But technically, I guess this one would come out and then repel. So they're contradicting themselves a little bit there. But anyways, wherever I got this from, I kind of forget. So that is just magnetism as an idea. Okay, that we've got, likes repel, opposites attract, fields, like it's similar stuff. Okay, and we have materials that can increase magnetism, and we have materials that can decrease magnetism, which means actually good time right now to actually I'm going to do electromagnetism a little bit, because the video talks about electromagnetism a little bit as well. So here's the big discovery. Back in the 1800s, Hans Christian Ørsted, by accident, serendipitously, which means like a happy accident, right? Accidentally discovered magnetic fields around current carrying conductors. So he was doing a lecture on a heating of a wire by electric current, trying to show people how cool electricity is and what you can do with it, or how hot it is, I guess, because heats up the wire. And he's just doing this, and he happened to have like a compass nearby because he probably liked physics toys like I do, and everybody does, I think. But yeah, he noticed the compass needle was changing when the current was turned on and off, and he's like, huh. So he investigated a little more and found that this diagram is a little bit misleading. They're usually arrows, but basically what would happen in this one, I'm just going to analyze depending on where it would be. You'd want to put this compass above or below. So if this compass is below, then this needle would actually end up pointing this way. Okay, and it's below the wire. So just to be more clear, specific about this, it's below the wire. And then actually, if you moved it above the wire, so above the wire, it would actually go the other way. So let's go up here, it would point this way if it's above the wire. This is what he found, okay? If you put it in front of the wire, it would actually go up. If you put it behind the wire, the north would point down. So you can see what's happening here. Even just this quick little analysis of this is actually a magnetic field like this around the wire. Okay, and that's the magnetic field. And we're going to see this on a dedicated page as well. But I just thought in clarifying where the compass is, it naturally kind of came out. Yeah. So this slide was dedicated just saying he noticed that the wire changes. So the fact that moving electric charges, this is if you're jotting this down or if you're just looking for emphasis in the files, moving electric charges, okay, create magnetic fields is known as electromagnetism. Okay, so moving electric charges create an electromagnetic field. It's known as electromagnetism, and that's how we make electromagnets. In 124, over near the pencil sharpener, has anybody ever noticed a little green duct-taped coil of copper wire that's attached to the ceiling above the pencil sharpener? Has anybody ever noticed that there?
Actually, yes, I've noticed that.
And of course, I guess I'm thinking of the question I asked to my grade 9s and 10s. You guys definitely should have noticed it because we used it for the demonstration for the projectile motion stuff. Did we do that in class, or did I just have to do videos online for that? Forgetting now. Anyway,
we did.
Yep.
We did videos for that one.
Okay, because we were online. But it's an electromagnet. In the videos, you saw the paint lid stuck to the electromagnet and so on. So it's just current flowing through, electrons flowing through the wires. That's two different things, by the way, sort of, right? Current flowing is technically positive flowing the other way, but in reality, we know it's electrons flowing. So you can kind of say it as a statement. But yeah, the current or the electrons flowing in the wire, either way you think of it, is charges moving, and they're creating a magnetic field. So this is Orsted's experiment demo. Hopefully it's a decent little video. Hopefully no Grammarly.
In 1820, the Danish chemist and physicist Hans Christian Ørsted performed a celebrated experiment demonstrating that an electric current passing through a wire could deflect a magnetic needle. The experiment can be reproduced by means of the following apparatus. A wooden base carries a magnetic. A wooden base carries a means of the following apparatus.
So they have probably that's current, like flow of positives, or is that, yeah? See how they have positive here on the left of the screen? They have a positive going up, positive going across. That's weird that they have a negative on the other side, but I think they're showing that that's a battery. Like if I had a screenshot of this, I would show like a battery, and so it's pushing. So this is the on the right side is the negative end of the battery, and the left end is the positive end of the battery. But with the way they show this, it kind of looks like, well, yeah. Think of this as flow of positives. I think you can probably see my pen wiggling there. So that's flow of positives, flow of positives, flow of positives. So the positives are attracting to the negative end of a battery, and the repelling from a positive end of a battery. Okay, so I'm just looking at this here and this here, and I was confused that are they showing electron flow or are they showing positive flow? So based on the way they're showing the north, this end of the north here underneath the wire, I can tell they're talking about flow of positives, And you'll be able to tell soon too, once we finish this stuff. So we just keep playing.
A wooden base carries a magnetic compass. A brass frame above the compass holds a thick copper wire with a small clip at each end. A pinion is used to raise and lower the wire above the compass needle
Too many
to
details
determine
there,
the
but-
relationship between its deflection and its distance from the wire.
So that's when we want to talk about the magnetic field strength, right? So he ended up investigating this a lot and found there's a relationship between how close the wire was to the needle, and so the magnetic field strength depends on the distance. But the main experiment, the main discovery was, that it changes. So when I do this in class, I can actually do this in class normally, where you have a wire with current flowing through it. Just hook up a 9-volt battery to it, and I have a compass. I have to have the compass sort of naturally sitting so that north is like towards the door near the hallway, as it turns out. So then I have to have the wire going perpendicular to that. And what happens is, as soon as you put electron flow or current or whatever through the wire, this thing actually lines up with the wire. No, wait, that's not right. You have to line it so it's in line with the wire, sorry. And then it goes perpendicular, of course, like I said on the other slide. I just messed that up there. Anyways.
Through which an electric current
they're showing the way the compass points when electrons are flowing.
3 leveling screws ensure that the system is perfectly.
I don't think we need to worry about the leveling screws. They're just talking about how he was super careful, basically. This one just be a little demo of it. Since I can't show you in person, I can show you videos. At least.
The rocket equation. It's a beautiful thing.
The rocket equation.
No astronaut launched.
Here we go.
Para repetir el experimento de Oersted,
Oh boy.
necesitamos un
This
cable.
is the kind of thing I can show in class. So he's going to line that compass up
Ponemos un
with the wire,
conductor encima de la brújula,
and then
paralelo a la aguja de esta
we're going
última.
to put
Y ahora, con
the
una pila de
voltage
9
across the
voltios,
wire, make electrons flow.
conectamos la batería
Come on.
al circuito, a nuestro cable. Encima, en vez de debajo del
So
conductor,
here we go. See it? As soon as he
la
connects the
desviación se
current,
producirá
the needle tries to
en el
deflect a little bit.
sentido
And
contrario.
if you use more than one 9-volt in series, you can get more voltage. You can get it to like jump right perpendicular. But that's the kind of thing. So you're seeing the
Si cambiamos la polaridad o sentido de la
discovery of
corriente,
electromagnetic induction in this
observamos que
video,
también
that the compass
cambia
needle
el sentido en el que se desvía
responds
la
to whether or
aguja.
not there's current
Si no
flowing,
tenemos-
which was very surprising at the time. It was surprising, and it was a pretty cool discovery. That's why they're saying it was a celebrated experiment, because it was like, wow, wait a minute. And they, of course, went with it and investigated and found a bunch of things. So how I'm talking about which way the compass will point, and in the video I could say which way it was, in the picture I can say which way it's going to go and so on, is this. Okay, this is to help remember the direction of the magnetic field. We're going to use right hand rules for flow of positives. Okay, I like to point out that we can equally validly use left hand rules for flow of electrons, and I actually think of it as left hand rule for electrons. There's an L. That's how I remember which hand for which. Okay, so L's for electrons, left hand for electrons. So these hand rules, as they're called, will help you figure out the directions of things, whether you're talking about positives or negatives flowing. So the right hand rule, if you point your thumb in the direction of, and you'll see, like, it's very common in a physics test situation around the room. If I'm supervising a test or whatever, you'll see a student like with their hand in front of them, the right hand in front of them, and they're pointing their thumb in the direction that the current says that it's flowing in the question, because current means positives, right? So it'd be right hand. And then they see their fingers curling. So their thumb points in the direction of current, or a conventional flow of positives. And then the fingers, you'll see them sort of curling their fingers naturally, not backwards if you're like triple jointed or something. Your fingers curl a certain direction naturally, and that's the direction of the magnetic field lines. Okay, so I have little pictures of that here. So I have my right hand. I had to flip my hand around from the way I was thinking just now, but you couldn't see it anyways. But so there's the thumb pointing in the flow of positives. The magnetic field is curling around the wire 3-dimensionally, like I showed on the other page. Okay. If you want to show this two-dimensionally, then there's the current that's going into the page, because there's the tail feathers of the arrow going away from you. So current into the page, point your thumb towards the screen, and then of your right hand, and your fingers should be curling in the direction of those red arrows. Okay. If we had current flowing out of the page, point your thumb towards yourself, and then your fingers should be curling in the direction counterclockwise there of the red arrows. Okay. So that's the first hand rule, and there's our reminder that X is flow up into the page and dot is flow out of the page, and it's the arrow, right? This is the tail of an arrow, tail feathers of an arrow, and this is the tip of an arrow. Right, so you got the tail feathers of an arrow, and you got the tip, and it would be going that way. So picture that going in and out of the page, like I said in the other one there. But sometimes repetition's good in case you missed it the first time around. So other pictures of this, or this is actually the left-hand rule. So if I talked about, these are equivalent pages, by the way, right? Flow of positives to the right is equivalent to flow of negatives to the left. So I'm using the left hand now, pointing my thumb of my left hand. Notice that the magnetic field is still going down in front of the wire. That sort of three-dimensional, whatever you want to call it, direction there, down in front of the wire on the right-hand rule, down in front of the wire still with the left-hand rule. Gives the same result. And these guys are still the same, right? When the electron flow goes out of the page, we've got clockwise. That's the same as positives into the page, clockwise. Okay, so left-hand rule gives the exact same predictions. There, you don't have to pretend that positives are flowing. You can use your left hand instead of your right hand, and you get the same predictions. Questions so far? Did I explain that well enough? I know I think my drawing is decent enough. You can picture what's going on here.
Sorry, I'm just a bit confused. Like when the fingers wrap around, like what's that representing again?
That's representing the direction that a north of a magnet would face. So in this little section here, if we put a compass here, then the north of the compass would point along the direction of the fingers. So it's really representing the direction of the magnetic field. So the magnetic field actually goes around and around the wire. Does that help?
A little. It's
So-
okay, I just have to look at it.
We're good or no?
Yeah, I'll just have to take a look at it later. I'm fine. Thanks.
Yeah, it's three-dimensionally coiling around the wire, and it's a little hard to draw that, but I'm showing like the arrow going across and then down in front, and then see how it goes dotted behind. That shows that the magnetic field's pointing up and behind. And so the direction of your fingers, of course, from your hand up through your finger is behind, and then curling around and down in front. I want you to visualize that. And so you can actually sort of see why you don't get like a piece of metal you have in your hand, if you have like a paper clip in your hand, it doesn't get stuck to. I actually coincidentally just happen to have a paper clip on my desk here, and it's beside some wires, but it's not magnetically stuck to these wires, even though electricity is flowing in those wires, because there isn't a north that's like pointing into the wire. It's actually going around and around, and it actually cancels out. So you've got a north here, canceling with a north there, and a north behind, canceling with a north the other way in front, right? So these actually, the net electric field in any spot from just a single wire, it's actually kind of zero, because it all adds up to zero. You can picture these two arrows certainly would cancel out, wouldn't they? Right? So you're not going to see things aren't magnetically going to stick to current carrying wires, just straight wires. Okay, because they don't have a net magnetic field in any location. So here's, what does it say? Example for a right-hand rule for a straight conductor. It says the direction of current flow is in the conductor is to the right. Use the right hand ruler. Why are they talking about that? So I guess this picture is sideways instead of, so it says to the right. I guess I better move that. Can I move it? Yeah, there we go. So it's saying the conductor, the electron flow, or flow positive, sorry, is to the right. Let me just move that behind, send it back. Well, I guess it makes it a little bit disappear there, but so again, using your right hand, you would point your thumb to the right, and then your fingers are curling up behind the wire and down in front. I could try to plug in the document camera to show my hand, but I think these diagrams, like it's exactly like this one here. You know, thumb pointing to the right, fingers curling up and behind and down in front. What is this? The actual chart. Yeah, the actual is flow of electrons, of course, the other direction. But so if you use your left hand now, point your thumb the other way, and your fingers still go up behind and down in front, using your left hand if you're thinking about electron flow. So I should say electrons left. There. Since the wording in the first one was to the right, the picture just didn't match it. To intensify, to make the magnetic field stronger, you can, instead of just having like one set of electrons going through a wire, instead you can coil the wire. Okay, so this is now we're going to talk about solenoids. And this, by the way, back here when I was talking about, you know, the magnetic field around a solenoid and so on, a coil of wire, when I mentioned coils of wire, this is now officially being tackled. So let's go back to here. Here we go. So if you have a coil of wire, right, a big coil of wire, and you got electrons going zipping around and around and around, instead of just having one wire with electrons going, you have like 400 wires with electrons going. And so what that does is it helps like add up a nice strong magnetic field, and it actually creates what's called an electromagnet. So the right hand rule for a solenoid is now instead, so it's a new hand rule. Okay, instead of pointing your fingers indicating the magnetic field and your thumb pointing up electron flow, instead you're actually going to curl your fingers of your right hand in the direction of the flow of positive charges. So they're showing here that this is flow of positives. So in the wire, in the coils of wire, we've got positives that are going like that, sort of, you know, clockwise, down in front and up and behind and so on. But so you'd curl your fingers in that direction. And then this core flux direction, they're saying north. That's the north magnetic field that's created by that coil of wire. And I put a yellow N there as well. Core flux. It's kind of really weird saying that, but so I have other diagrams of this. So I have a coil of wire. You got I have to turn my hand around backwards here to visualize this, but I'm curling my fingers in the direction of the flow of positives. My thumb is pointing towards the right with the north. If a little bit easier anatomically here to arrange my hands, I can, in front of me, I can coil my fingers in the direction of electron flow, which is the opposite flow direction as the positives. And still my thumb points to the right, correctly saying that we've got a north. So I'm literally saying these are equivalent, right? You've got a north and you've got a north, whether you're talking about electron flow or positives.
I have like a really basic question that I should know, but can you explain again how you know like what direction they're going, like negatives and positive flow?
So that back when we, like I would show, let me just show in this diagram, or which I'll start here anyways. So if I had a battery, and if they're talking about flow of positives going this way, then that would be that we have hooked up a positive to this side of that wire, so that in a battery we'd have a positive side and a negative side. And so we would have just hooked up a battery, and positives would repel from positives, right? And so you'd have positives going to the right if I hooked up a battery that way. Okay. So when you're analyzing this, if you did this with a 9-volt battery, hooked up the positive side to here and so on, you'd be able to say, okay, I know positives theoretically are going to the right. And so my right hand would say, oh, okay, my fingers are going to curl and predict this red magnetic field direction, right? If I wanted the positives flow the other way, I'd hook the battery up the other way. Okay. Equivalent to all of this would be, instead of positives flowing to the right, we would say, oh, well, in reality, of course, electrons are repelling from the negative. And so we actually have electron flow this way, right, to the left. My pen's not working well there, but electron flow to the left is equivalent. And my left hand rule will give that same prediction of that red magnetic field. So it's all about which way you've hooked up the battery.
Okay, that makes sense.
Perfect. You're welcome. All right, so electrons going in a circular path, right? Electrons going in a circular path. So picture the circular path of your curled up fingers here, right? Create a field that points orthogonal to the plane of the circle. Kind of a fancy word for perpendicular. It's like three-dimensional perpendicular, okay? So picture the electrons flowing in a circle this way. Let's go around and around three-dimensionally this way, right? Then we've got a north that points up from like the center of the circle, like that. That's what's called orthogonal. It's orthogonal means that it's at 90 degrees and this angle. Oops, I'm using a line tool still. Back here. So at 90 degrees to that part of the circle, it'd be at 90 degrees to this part of the circle. I'm trying to draw in 3D, you know, it'd be at 90 degrees to there, you know, like that's orthogonal. 90 degrees all the way around. So the question that I want you to think about, if you had electrons going around and around, it's going to make a north. What do you think causes materials like iron to be magnetic? What is it? To be clear, what I'm asking here, what is it in the material that makes these little norths that point to the right and up and down and so on? What is it that's actually, what is it that we know that has electrons going around and around? This is not a hard question. Anybody? Materials, substances are made up of some. No. Think. You know, like what is all iron made up of? What's the smallest piece of iron you can have? Break any.
Like we're talking about like how an atom is made up of different parts.
We're talking about atoms, right? So we're talking about iron. If you break down iron into smaller pieces, the smallest you can have is an atom, right? And so we're talking about where have we, this is another hint, where have we talked about electrons going around and around? Of course, it's atoms, right? So if someone's asking like, so what causes magnetism? The answer is actually electrons going around and around in atoms, okay? So that picture is this. Picture an atom where we've got protons and neutrons in the middle of the nucleus, right? And then you've got electrons going around and around. That electron movement is going to make a magnetic field, right? So the magnetic field direction, as I pointed out on the other page, would be up for this atom. Okay, so we can go back to that diagram of this here, right? And this is like all of the atoms are all kind of aligned the same way so that their magnetic fields all point the same way. And now that's really magnetic. Ferromagnetic materials do this easily. Non-ferromagnetic, like paramagnetic and diamagnetic and so on, they don't. We're not saying why, we're just saying they don't, right? It's just something to do with how their atoms are bonded together and whatever. So yeah, those electrons going around and around make a north up. And so domain theory explains sort of why some materials are magnetic and some aren't. It doesn't really explain, but it says, in a material where they all line up, then it becomes magnetic, which is very, very obvious. Whole bunch of norths adding up to a strong north, all pointed the same way, right? So I would say this page conceptually is pretty important. Just knowing fundamentally that magnetism comes from the movement of electrons in atoms. Okay, pretty fundamental. And it came naturally from us talking about Hans Christian Ørsted's discovery that flow of electrons, wherever it was up here, flow of electrons causes magnetic fields. And then we just gradually worked towards the idea of coiled conductors and got the idea of magnetic fields from electricity. Okay. Try and show something just briefly here. Picture a wire that's coiled like this. I'm going to picture a wire that's coiled like this. And I want to have, let's just go more realistic strategy here and talk about electrons flowing. Okay. So I'm going to look at electrons flowing in 3 different sections here. Okay. And I want you to think of the left-hand rule. So just think for yourself for a second about what the direction of the magnetic field is at each of these spots. Okay. So just use, so you're on the right track with me, just use this analysis. Electron flow through a straight wire. Okay, so we've got 3 sections of straight wire left-hand rule analysis. So what way is the magnetic field at this section right here? And specifically, you could answer if you want that what's the magnetic field here inside the wire, like onto the front of it, I guess, and what's the magnetic field like behind the wire here? You know, picture like, you know, looking in front of and behind the wire there. So which way is the magnetic field in front of the wire? Anybody?
Is it like, do you mean like it's vertical? Like, is that what you're asking?
Yeah. Yes, vertical. Now up or down?
Oh,
Mm-hmm. Do you have an answer?
Up?
Point, yeah, did you say up? Yes. So your thumb's pointing along the green arrow there of your left hand, and then your fingers are curling around and up in front, right? So that means that we can say this must be up here. And then this one conversely is down and behind, right? So I want to visualize a magnetic field that's kind of like this, right? Where it's, you know, around and around, but specifically up in the middle and down on the outside. And then, you know, it's pretty easy to sort of do that again, where it's like up in the middle, down on the outside, up in the middle, down on the outside. And so what happens is we end up with all of these ups add up. These add up to a nice strong up north in the middle. Okay.
Sorry, would the shape of this kind of be like if you're doing like a thumbs up with your left hand? Is that kind of...
So there's two different left-hand rules I'm talking about here. So first of all, I'm just talking about the main, the basic, you know, flow of electrons in a wire, right? So I'm not even talking about a curled conductor here. I'm just talking about this one. So let me actually take a screenshot of this one right here. I just want to try to help you see what I'm doing. What I'm actually talking about showing or whatever is that this is the fundamental Oersted, you know, discovery, right? And so this other left-hand rule that we're talking about with coiled conductors is actually a result that's true, but I'm kind of proving that it's true. And I'm trying to prove that it's true based on the original one. So I unfortunately have to sort of, actually, I think I could show like this diagram, this left-hand rule diagram works well for this bottom location, right? Because we've got the up in behind the wire, and we've got the down in front of the wire. So you can see that analysis there, right? That makes sense. And then I'd have to invert the diagram, I suppose, and have the thumb pointing the other way at the top and so on. But picture the analysis we've gone through. What I'm pointing out in the end here is that they add up to control group. They add up to a nice strong electromagnetic field in the middle. Okay, they add up to a strong magnetic field in the middle because you have a whole bunch of norths pointing up in the middle. The outer ones, it's like they're separated. One's way over here and one's way over there. They're not adding up as much as the ones in the middle are. Okay, so notice that this actually goes along with the idea of, I'll show you a little trick here for visualizing. So picture a paper towel or a toilet paper roll or whatever. Come on, like that. And then picture a wire that goes, you know, around in front, and then behind it's coming out like this, and then it goes around in front, and it goes behind and around in front. So we've got a bunch of coils of wire, right? So this is essentially the same situation. It's just this is analyzing one of the coils. So if I have electrons going this way in the wire, that means I have electrons going, you know, all the way along. I have electrons going like that and around behind and then in front and so on, right? So if I use my left hand for this, I end up having my hand in front of me, my left hand in front of me. I have my thumbs pointing up so that my fingers can curl in the direction of the green electron flow. And what I end up with is this nice strong north arrow. Okay. Because not only are all of these norths adding up in the center all the way along through all 360 degrees, also the norths from every single coil of wire are all adding up as well. So picture a bunch of norths from this one, right? and then a bunch of norths from this one. So what I'm doing right now, I think there's another page dedicated to this, to be honest, but it felt like doing it right now. In the middle, there's a whole heck of a lot of north arrows pointing up. And so that's why you get a nice strong electromagnet when you run electricity through a coil. Is that good? Just a whole bunch of little analyses of this main left-hand rule. And then, of course, in order to make coils a little easier to analyze, there's this other left-hand rule, right, that applies to coils directly, and it's just convenient, right, to be able to say, oh, so you can analyze this at each degree, and they all add up. So you do that, or you use the combined, rule for a coiled conductor. Okay, but that's this result here is really because of the original one. So the direction of current flowing through this solenoid is shown using blue arrows. And again, this is the battery here, and we've got positives that are repelling away, right? The positives repel away from the positive. So they're saying we've got current. Notice it's current here, positive flow. Right, we've got current flowing like that. And so that means you're like, okay, I have to use my right-hand rule. So I'm going to curl my fingers in front so that they go up and behind and down in front. That's automatically making a north to the right. So your fingers should coil down over the solenoid, and the side closest to you, your thumb ends up pointing to the right. And it actually was already kind of listed there anyways, but that's what you want to be able to do. Draw the magnetic field lines around each one. Maybe I'll just reveal this on the next page. You can try it on your own and make sure you can get those correct answers later, okay? So it says that if the white tip of this compass is the north, so we've got the north here underneath the wire, which way is current, meaning positives, flowing? Okay, so you want to think, okay, I'm talking about positives, and so I guess you'd sort of think about which way your fingers must be going to make north point that way underneath. And I think you should have an answer there where your thumb would be pointing this way so that your fingers can be curling underneath the, I'm trying to draw a hand there, but your fingers would be curling underneath the wire, and then up and around, one like kind of like that, right? And so I think we're going to conclude that it'd be to the left, right? Analysis that we now know and use and understand and so on as we get used to it. So these ones here, you can draw the arrows, the directions based on that. There's solutions for it later for you to see. So that is magnetic fields and electromagnetism. And this is still in your 4U textbook, this stuff here. So the 1 to 7 solutions are all done and will be posted along with the PDF of this lesson. Any questions at this point about magnetism? You're going to find, I'll just load up that homework solution for you so you can see it's not lesson 20. Lesson 20 PDF answers. A ton of, like, notice there weren't any equations, right? So it's just sort of understanding like what happens when, and so on, drawing pictures of domains and so on, explaining ideas and concepts and so on. Okay, and the left-hand rule of a coiled conductor and so on. I even did this question A here in the lesson itself to help you out. So it's just big kind of idea concepts rather than obscure equations that we just have to add to the list and get good at using. So 21 talks about forces on moving charges. So this is different than what we just looked at. So we're actually going to relate two things, right? So we're going to talk about how to get a magnetic force to affect a moving charge, and just keep, basically analyze and figure out how that works. So magnetic force on moving charges. Okay, so these charges have to be moving in a magnetic field. So there's some in this page here, there's going to be some, this has to be true and this has to be true and so on kind of things going on here. And so this is the main statement. Okay, magnetic force on moving charges, they call the motor principle, okay, because it's how motors work. And really what we're talking about here is that there's going to be a magnetic force, right? So it says a magnetic field can exert. So the can is, there's a note to do with that, but it can exert a force on a moving charge. Moving is emphasized there because you're only going to get a force if the charge is moving. Okay, and I'll stay on this page a little bit for you as we go through this. But the motor principle, right, is that a magnetic field can exert a force on a moving charge or a current carrying conductor, and obviously. So it can be just a charge moving through the air, like an electron beam, or it could be electrons moving through a current carrying conductor. Either way, you've got a moving charge. Okay. The can is that it depends on angles. Okay, it doesn't always happen. There has to be certain angle requirements. The angle has to be 90 degrees. The magnetic field direction and the motion have to be at 90 degrees to one another to be maximum, that is, anyways. But we'll come across the details of that later. For now, you can just say it depends on the angles that things are moving. So I just want to point out that this force they're talking about is similar to this is what is also referred to as Lorentz force. You're hardly really ever going to hear that. I barely even remember that it was called Lorentz force, to be honest, because it's not talked about very often. But I really want you to realize that that's also referred to as electromotive force, or EMF. If you have a really good memory, I've already talked about that a little bit, but I'm not gonna mention it right now because it's gonna come together later. But so it's an electromotive force. It's a force on electrons. It's a force on charges, right? So they call it electromotive force. So the force, if you end up, so you can have a wire that ends up with a force on it, like the wire actually pushes to the left or the right. You're going to see that shortly. The force that's on a conductor is actually a result of the forces on the charges inside of the conductor. And so you're going to see, or at least a drawing of the idea of a wire actually gets pushed one way or the other. That push is due to the push on the electrons itself in the wire. Since the electrons are trapped in the wire actually physically moves. That's this diagram here then. So if these electrons were getting pushed to the right, because of a magnetic field, then the whole wire would actually experience a force to the right. So what's your strategy here right now? Are you copying here? Do you need more time on this page?
Just a bit. Yes, please.
Yeah, I will wait.
While people are copying, I thought of a question.
Sure.
So, like, the perpendicular orientation of the compass, like, is that like to do with like the 90-degree like wave angle between the electric and the magnetic one?
Yes. Good job.
Okay.
Yeah, good job. And even here, it's a little bit hard to draw, but picture, I could draw it two ways here, the magnetic field. I could show the magnetic field like this, which means like into the page. So this is the, I'm just going to say magnetic field. I was going to do B because that's the symbol that's used. We haven't done that yet. So magnetic field into page. So if the magnetic field's into the page, picture your left-hand rule here. You'd have the, oh, we didn't do the left-hand rule for this yet. So I can't actually do this yet. but I'll come back to it. It works. So come back to it. Okay, but picture if there's a magnetic field to the right on those electrons, that wire would actually experience a force to the right. The wire would physically move to the right. That's a really neat little demo that I do in room 124 when we're there. I have a wire, and it's between two magnets, really strong magnets, and when I put a current through it, the wire actually moves, to the left or the right kind of thing. Pretty neat. Are we good with that page? I'm not referring to page McCord, by the way, this page of the lesson.
I'm not sure about page.
Every time I say page when you're in my class, I'm always like, I wonder if you're like, oh, there's my name. All right, you're used to it, eh? So the right-hand rule, we'll come back to that page and explain that in a second. But so the right-hand rule for the motor principle, okay? So in this rule, you're not curling your fingers. Your hands stay flat, like a karate chop kind of thing. Your fingers point in the direction of the magnetic field. Your thumb of your right hand points in the direction of the flow of positive charges. Okay, so in the direction of conventional current. Or, of course, we could use the left-hand rule, but let's stick with the right-hand rule for now. Right, so picture your right-hand rule, pointing directly forward, let's say, and if the current was up, then your palm of your hand, if you're to like go and slap someone, pushes in the direction. So your push in the direction your palm naturally faces. So there'll be some pictures of this in a second here too, but like that. There we go. So this is fingers pointing in the direction of a magnetic field. So this right hand has the magnetic field is to the left. The flow of positives is up. And then that palm, picture of that palm of that hand is coming towards you and push towards you. And so the outward facing palm means there's a magnetic force out of the page. Okay, so the magnetic force there would be out of the page. So we have to try and think three-dimensionally when we go through this stuff. We can do this. Okay, so that's the new right-hand rule. Perfectly equivalent left-hand rule. Use your left hand, point your thumb in the direction of electron flow, and in this case, the hand would be pointing, it would be left hand, your fingers would be pointing to the right. Your fingers would be pointing, so I have to contort my body a little here, move my hand to my left side, I guess. So I have my, magnetic field is still to the left. My thumb, I have to contort my body to make my thumb point down. So I have my hand to the left side of my body. I got my fingers pointing to the left. I've got my thumb twisted, my hand twisted so my thumb points down. Your palm should be facing towards you now. So usually this isn't mentioned. Where I was taking this information from, they actually even mentioned it. So most textbooks, most courses don't mention it, to the point where I was having a discussion with my brother-in-law over Christmas break one time, and there was a neat little motor that I'm going to show you soon that we were analyzing. I wanted to analyze how it works, and so I was talking about, okay, left-hand rule, electrons are flowing this way, and because I had a 9-volt battery hooked up when we made the little motor and we were using it, and he was adamant that we had to talk about positive flow, right-hand rule, current, but you really don't have to. Left-hand rules work great. So this is us analyzing how a little electric motor works over Christmas holidays. Nerdy. It was fun. Anyway, so if I go back to this, I used the right hand or the appropriate hand rule to look at which way the flow would be. So I had the magnetic field pointing in. So I've got a karate chop hand going here where my fingers are straight pointing into the page. I've got my thumb pointing up, and my palm of my hand is, I would slap to the right. You follow me there? Do I need to plug in the document camera, or are we good?
I didn't really get that. There.
Like if it's a lot of effort, we're okay, but it might be nice to see.
Okay, I will try. Give me a moment here. I need a moment. Document camera. It's a very physical thing, right? So here we go. Camera, document camera. Let's see here. There we go. Here's my hand. So that is my left hand. And now if I were to zoom out here, focus or zoom? That's focus. I don't know if there's a zoom in this thing or not. I guess like this. So let me go out. No, as far as I go. All right, so I need to move this little thing down over here so I can show what's going on. All right, so my fingers are pointing like down into the desk, right, into the page, and then my thumb is pointing up towards the electron flow, and now the palm of my hand is slapping that way, if you follow me. Okay, so electron flow is my green arrow for electrons. My fingers are karate chop pointing towards into the page. That's the X's for the direction of the magnetic field. And then boom, the push is to the, I have to slow down a little bit here, but the push is to the right. Does that help?
What does the push represent again?
The electromotive force, the push on the electrons. The Lorentz force, the motor principal force, the electromotive force, the EMF, they all mean the same thing. Isn't that great? But yeah, that's the push on the electrons. So the left-hand rule for electron flow is the exact same, which is you're going to use your left hand, just like I showed you, right? The left hand fingers point in the direction of magnetic field, the thumb points in the direction of actual electrons, and your palm faces the direction that you would push. And so I took that picture and I like inverted it. So this picture showed right-hand rule, magnetic field to the left, positive flow up, green push towards you. This one's going to show magnetic field same direction, but electron flow down, right? So electron flow down, positive flows up, same thing. So either way, the palm is pushing towards you. And I have manipulated this picture to show that. It's actually the same picture, you know, copied and pasted and flipped and whatever. But that direction is still out of the page. So the demonstration I show in class is similar to this, a little bit of a different construction, but strong set of magnets, a wire, we've got a conductor, and so analyze here. I'm going to have, maybe this might be a good idea again here. So I just have to move this over enough that I can see both my hand and the unit, this situation here. So that'll work. So I'm going to say, okay, I've got electrons flowing, hang on now. Electrons are actually flowing the other way. So let's use the right hand because this arrow indicates flow of positives. And we can tell because positive side of the battery, positives flowing up through here, through there, up and around. It's just a circuit, right? So I've got electrons flowing this way in the direction of the wire, right? And now I need to point my fingers in the direction of the north. So that means I have to like straighten my fingers out and I have to contort my body so that the fingers are pointing up in the direction of the magnetic field. The magnetic field is from the north down here up, right? So the north direction is this, from away from the North Pole towards the south. I thought of a thing that sometimes people say, like for direction of magnetic fields, is it's like a Canadian vacation. Like in the winter, March break, you know, you leave from the north and you go to the south. So that's the direction of the field lines, but you know, it's really the north repels from the north. So anyways, flow of positives, magnetic field up, and then see how my palm here is pushing to the right. And so we're actually going to have a magnetic field, or magnetic force this way. So this is FM, let's call it, magnetic force, pushes on all of the electrons to the right. And so all of these magnetic force pushes on the electrons actually make that wire, would make the wire swing out to the right when I connect the current. And then when I let go of the current, it would swing back to the middle. And if I connected the current the other way, it would swing to the left by the same kind of analysis. Pretty neat stuff. So I don't have it set up by hanging by a wire. Certainly could, I've just never thought of it. Instead, I have, give me a sec here so I can get this thing out of the way. In the way I demonstrate in class, I just have a section of wire that's stripped, and it's sitting on two other wires that have a stripped section. So it's sitting on wires like this, and it's free to roll left or right. And it does just that. It rolls left or right when I connect the current in various ways. It's pretty neat. I was actually quite surprised when I first, because, you know, like, people didn't demonstrate this kind of thing to me when I was in school. At least I don't remember. Maybe I wasn't paying attention. But, you know, I was a bit surprised in room 124 back in like 1999 or 2000, year 2000, when I first started working at Rideau. I set up this hoping I could show the motor principle actually for real. And I was quite surprised when I was able to get it to move left or right, no problem. It's a lot stronger force than I was thinking maybe it was. This guy explains all of it. So this is, you know, if you're not seeing things, and I did use the document camera to help us see things, but he's, you know, so you can visualize the left hand and the right hand rules and that. So I don't know if I'll play the whole thing here. So you can't, or no, you can, because the, no, the microphone. Can you guys hear it right now? How about now? I think the new microphone, the good microphone.
I can hear it.
Now it's going. So he's showing, like, you know, flow of, I'm assuming that's probably electrons the way he's showing it. This is flow of electrons here, and I know because my thumb would be pointing in the direction of electrons on my left hand. My fingers are pointing down. The motor force is to the, you know, sort of to the right, three-dimensionally, or sort of like that. So he's talking about all the rules here. So at some point he's going to show his hand.
It's sort of like a 3D drawing. I've got the flow of current this way, and I've got a north and south pole of the magnet.
He's saying current.
If current is flowing, then this magnet is going to influence it to be pushed in some direction. And the direction of that force, which we call the motor force, is out.
So he's wrong. That wouldn't be current. That would have to be electron flow, because it has to be my left hand in order for my push to be that way, because he's got the north here. So he's mistaken as to whether or not that's current or that. But I'm surprised, because he does talk about left hand rules and right hand rules in there too. So, but at least you can sort of picture when he shows his hand in position and so on. So the video may or may not help you. It's a little bit wrong in terms of which kind of current flow it is, or whether it's current or electrons. So this is where you're excited to hear, I'm sure, that we can reason out a logical equation for this. And so we're looking for an equation for the magnetic force on a moving charge. And this is really good, real kind of, I'm being very realistic about how scientists would do this, okay? So they would say, okay, well, what do you think is going to affect the size of the force, right? So for example, you know, to start us out, if there's more charge moving, obviously there's going to be more force, right? What else? What if there was more velocity, like if they're moving faster, right? Then that would be more force too, of course, wouldn't it? What if there was more magnetic fields, more magnetic field strength? So we're talking about a magnetic field that's near this. If you use stronger magnets, what would you think that would do to the force? Of course, it's going to give you more force, right? It turns out part of this result was that if that's the angle stuff now being detailed, right? Turns out if there's a 90 degree between them, which absolutely does link back to the 90 degree angle between electric fields and magnetic fields, 100%, Sarah. So it turns out that if you're at 90 degrees, the motor force is a maximum. So basically the scientist's job at that point would have been to say, okay, wait, if 90 degrees makes the force be a maximum, what function do we have in math that makes that happen? And of course, the answer is sine of theta, right? The sine curve is the maximum value of 1 at 90 degrees. So for directly proportional to charge and this, you know, the velocity of it and the magnetic field strength and the sine of the 90 and so on, this formula makes sense. We've got charge, we've got velocity, we've got magnetic field strength, B. So I'm going to just show the definitions here, because B is what they use as the magnetic field strength. The units for now are listed as a name after Tesla, T for Tesla. Okay. I'm going to show you for real what that is. Just like saying, like, instead of newtons, we're talking about kilograms, meters per second, but T is Tesla, and we'll look at what those units are soon. Okay. In fact, we're probably going to do that in the very next page. But anyways, that's a formula that no one can deny the logic of it. We know if there's more charge involved, then it's going to be more force, of course, just logical, right? The force is coming from charges. You're adding up a bunch of charges, but there are a bunch of forces. And if they're moving faster, if motion matters, then it's only logical that more motion is going to cause more force. If the magnetic field's causing the force, it's only logical that more magnetic field causes more force. So this equation is very much based on the reality of what we find when we look at this. So that video that showed the wooden apparatus business and so on, this one, darn it, I think I closed the one that I wanted by accident, to be honest. But the one with the little wooden apparatus, and you can move it closer and so on, that's what he was discovering, he was looking at. So there aren't vectors over any of these things, but force and velocity and magnetic fields all have directions. We use the hand rules to determine the direction. So they don't put vector symbols in there, even though this really is a vector situation. So the idea of the vectors comes from the hand rules. And so they're picky. They don't put the vectors on, even though there really are directions. Okay. So, right, the hand rules determine your directions. Okay, so you're going to see, an example where they, what is it here? Somewhere here. I don't know, wherever. Anyways, if I gave you, if I gave you these values, you can plug in numbers and figure it out, right? So if I gave you, 2 coulombs of charge go, and they're going at 10 meters per second, and the field strength is 2, you just multiply to get your number. No big deal. The bigger deal is recognizing that there's an equation for it, pulling out the correct equation, using it. Okay, so make sure to make note of the magnetic force on a moving charge is this formula here, like this page shows. So I just want to talk about the units. They call it a Tesla, but what are the actual units? What is a Tesla? Well, really, we would just want to solve for B, right? The magnetic field strength. That's new to us. We just saw 2 minutes ago that B is magnetic field strength. So if I solved for B, I would divide out the Q's and the V's. I don't have to worry about the sine theta because there's no units. So I'm just going to pretend I just get rid of the, as far as units go, it doesn't have anything. We're just analyzing the units. So we need to think about the units for force, the units for charge, and the units for velocity. Units for force are obviously newtons to start out with. I have the equation version there, but here we go. So the units for force are newtons, of course. Units for charge, we know are coulombs. Units for velocity. What are the units for velocity?
Meters per second.
Oh, good job. Right? So we've got newtons, we've got coulombs, we've got meters per second. So we have to analyze a little further where we're like, okay, wait, what's a newton? A newton is, of course, force, right? Force equals mass times acceleration. So what are the fundamental units of force? Mass is kilograms. Acceleration is meters. Yeah, got it. Meters per second squared. Okay. So in the next line, I'm going to replace the n with kilograms meters per second squared. Okay. So this unit analysis is to figure out what the heck a Tesla really is. So there's my newtons. There's my coulombs. There's my meters per second. Algebraically, I can divide by that fraction by inverting and multiplying. So I'm actually going to show, and this is still a divide by coulombs, right? So I'm going to have this stuff. I'm going to have a divide by coulombs, and I'm going to have a multiply by seconds over meters. Right? So there's the numerator. There's the denominator, essentially, the divide by coulombs. And then there's the invert and multiply. Okay? So what happens at this stage? Can you tell? For units and so on? Notice there's a mass in the top and a mass in the bottom, right? Mass divided by mass. The order doesn't matter here, right? So I could rearrange this so that it was kilograms, mass, seconds in the top, and then in the bottom I could say, oh, let's the mass is in the bottom, so there it is, and the seconds squared is in the bottom, and the coulombs is in the bottom, right? So it kind of makes it easier to see that mass divided by mass is a 1, so they cancel out. So I show this logic simply like this. Mass divided by mass goes away, and then here, seconds squared means second times seconds. I'm green now apparently, right? So 1 of the seconds divides out. And so what happens is the square, I'm showing the square cancels out. Okay, so that this is showing what these why these cancellations, these simplifications make sense. So magnetic field strength is left being kilograms and coulombs and seconds. So kilograms per coulombs seconds, which is what's listed in books and so on, kilograms per coulombs seconds. Weird, but so you can kind of see why they call it a Tesla, because that's not going to make much sense to people. Whereas like velocity being meters per second, it's very, very logical. So they call it a Tesla. Okay, so just putting in units that we know, and that's why we've always kind of focused on that SI units, kilograms, meters, seconds, and so on. So we're putting this fundamental unit, or this unit of a magnetic field strength, in terms of fundamental units, kilograms and seconds. We had to have coulombs in list too. So from now on, I should be saying SI units, meters, kilograms, seconds, and coulombs. All right. Magnetic force is always perpendicular to the velocity of the charged particle. Oh yeah, since the magnetic force, the way we're describing it, because it's always like the palm pushing to the right and the other ones were up and into the page or whatever, since the push is always perpendicular to the velocity, then that means that the magnitude of the velocity isn't going to change. It's just going to determine, it's going to change the direction, okay? So this, what I hear, sine of the angle between the velocity determines how much force there is, right? But the idea is if we have a velocity, v, and we've got a magnetic field sideways, then we know there ends up being like a maximum magnetic force that's into the page, but it's that force is perpendicular to the velocity, okay? And then I was jumping ahead to a different point here, but you know, like we look at we could have the velocity at a different angle, and so there's a smaller angle between the magnetic field and the velocity, in which case the force into the page is going to be smaller. It's going to be the sine of 30 degrees, for example, which is half, right? So this magnetic the force on this charge would be half if we have a 30-degree angle of what it would be if there was a 90-degree angle. So that's just a little more detail about the angles. Larger than 90 degrees works too. If we're at 130 degrees, well then that becomes equivalent to, because that's 90, and then 90 up to 130 would be 40 degrees. So that would be the same as doing like sine of 40. I think if I did the numbers right there, if that was a 130. Even bigger. If you get a negative result from sine, picture the angle being 220 degrees. That's 180 here, right? And so that's the same as having a 40-degree angle. And so it's going to be based on the idea of a 40-degree angle, but you can see that it's going to be the opposite direction. The force is going to be, the magnetic field is going to be out of the page, because in the equation that we already just know here, we know now or whatever, let me just grab a screenshot of that. If I did, oops, that's not a screenshot, oh, a screenshot. Remember what I'm trying to do here. All right, grab that, bring that over here. If I had a 270, then on your calculator you'll find that sine of 270, right? If I put a 270 in here, then this result ends up being a negative number, and that shows us that it's going to be the opposite direction. So it basically shows that instead of the force being the way the hand rule would predict, you're like, ooh, it's the opposite direction because of the negative. Okay. Plus, if you did the hand rule itself, you'd sort of see, you know, that your thumb pointed the other direction. You had to contort your body and move your hand so that your thumb could point the opposite direction. Here, the thumb was pointing this way, you know, or up in this case, for example. And now we've like rotated around the other way. Clearly, that changes the direction of the force anyways. So this is the mathematical equivalent of the force being the opposite direction. What do I have here? Yeah. Oh, this is the part that I thought I was talking about. So since the magnetic force is always perpendicular to the motion, it's not going to change how fast it's going, the size of it, the magnitude. It can only change the direction. So for example, if a velocity going this way has a force to downwards, it's actually going to change the path. It's actually just going to change the direction to be going this way, and then finally, you know, down when it gets to the very left, right? So this velocity has a force that way. It curves the thing to here. Now it's got a velocity down. The force as a result is still 90 degrees to it. If you analyze the hand rule and so on, this is for, let's say, an electron going left-hand rule, electron magnetic field is out of the page. So this is for a magnetic field out of the page. I have to analyze what direction that is. So magnetic field probably says that somewhere. That doesn't really say that. Magnetic field B is out of the page. And so my hand rule helped me figure that out because I analyzed like what direction the field must be for the force to be the way they're saying. Yeah, so it ends up in circular motion. It's the same as having like a planet out here or a moon, let's say, taking the force of gravity acting towards Earth. It just turns it so that it goes to here, and then turns it so it goes that way, and turns it so it goes that way, and so on. Okay. Cultural significance of the look of this is completely unintentional. It bothers me, but it's velocity, it's force, it's curving, changing its path. So as I've analyzed, if you're thinking of electron movement, it would have been clockwise. Hang on, no. Man, maybe it's not out of the page if they're saying positives are going that way. Positives are going that way. Magnetic force is down. It's actually into the page because they were saying, I was thinking electrons. So the magnetic field is into the page because they were talking about flow of positives. Because of course that's what we're supposed to do in air quotes, but everybody knows it doesn't really matter. You should know that it doesn't really matter. So this would be an X here because this was positives going that way. So with your hand rule, put your thumb of your right hand in the direction of V at the top, and then make it so your palm is pushing down, right? You should have your right hand out in front of you with a karate chop kind of a look with your thumb pointing to the left. Your palm is naturally facing down with your right hand, right? With your left hand, you'd have to have your thumb pointing to the right and your fingers pointing into the page. Either way, your fingers are pointing into the page for the magnetic field. So this, interestingly enough, I hope you find anyways, this is how they determine the mass of an electron. So they put a charged particle, known charged particle, through a magnetic field and make it curl in a circle. And the circle, radius of the circle, you can end up calculating out the mass of the object, and that's how they get the mass of an electron.
Because we're going to show you the charged particle beam doesn't need to go in a circle when you put it in the uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun. An electron gun really just means heated metal filament. It's easy to draw electrons off of. Here's the gun that you can now see glowing orange. It's a little metal plate. We put in a large positive position.
So just jump ahead and you'll see the beam actually going in a circle. It's for the same reason. So there's the beam starting out. And eventually you're going to see a curving of the beam. There we go. See how he can make the electron beam curl just by putting a magnetic field near it. Pretty nifty.
What we're here to do.
So if you put a uniform magnetic field in, eventually probably shows the idea of curving it into a circle. So once you have that circle, you can measure the radius of the circle. You can figure out how much force it must have on it. You can figure out what the mass of the particle is. And that is how they figured out that 9.11 times 10 to the negative 31, by knowing what kind of force we have on things. Okay. So the only other thing is basically to say force on a current carrying conductor, but man, we only have 5 minutes left. So I can't do all that. So we are going to put a pin in this lesson and finish it tomorrow. Okay, so you can certainly try some of these. I'll put the answers up. But when you get to questions that are to do with force on a current carrying conductor, we haven't done those specifically yet. But yeah, so I cannot finish this one today. Oh, well, right? We can slow it down a little bit. But neat ideas, right? Magnetism overall, and then now there's some equations and concepts to do with the force that results on a moving charge in a magnetic field. So we talk about magnetism, and then the resulting forces on charges. So those are kind of our 2 topics for today, except we didn't finish it. So I will stop the recording.
Oh, before you do, I have another question. Sorry to delay everyone's lunch. I'm not really sure why the current goes in the opposite direction from the electron flow.
It's actually a silly thing, right? They describe in this, like if I hook up, where's the picture I hooked up with a battery? Right here, this one has a battery. So if we're talking about actual flow of electrons, then of course they repel from the negative, right? So we've got electron flow. That's what I'm actually going to be referring to it as, is electron flow, right? So we know in reality electrons are going that way. If we think about a hypothetical doesn't actually exist positive test charge, which way would it go? It would repel this way, right? So current hypothetical doesn't actually exist flow of positive charges would be the way the red arrows are pointing, and then actual electron flow is the opposite direction by logical definition. Does that help?
Yeah, that makes sense. I forgot about the test charge thingy. Thank you.
Yeah, you got it. Test charge. So it doesn't really exist, but we talk about it for some reason. Yeah, that's it. Excellent question. Cool. All right. So 1 o'clock, I'll be back on if you would like some help, and otherwise have a good rest of your day.